keeping a tight schedule. Our next speaker will tell us his name because I cannot pronounce it and I apologize. He is going to speak to us about environmental degradation effect of high temperature water and hydrogen on the fracture behavior of low alloy reactive pressure vessel steels.
Thank you so much for the nice introduction. My name is Dai Qingxue. I come from Paul Schaeffer Institute in Switzerland. Today I'm going to share with you some interesting results in my PhD thesis with the title of Environmental Degradation Effects of High Temperature Water and Hydrogen on the flusher behavior of low-alloy reactor pressure vessel steels. And that will be a quick introduction to the background, followed by the materials and experimental procedures. Due to the limited time, I will just talk about three kinds of reactor pressure vessels with different properties. And in the end, there will be a quick, brief conclusion. So here is a figure describing the components in the nuclear power plant. And this part is called the reactor pressure vessel. And this reactor pressure vessel contains the fission products. And because this part cannot be replaced, so it is actually the most critical component in nuclear power plants regarding safety and lifetime. And usually this part is reactor pressure vessel, or RPV, and it is mainly composed by the low-alloy magnetic steel. And the flusher behavior of the reactor pressure vessel could be reduced by the high temperature water and the hydrogen in the coolant. Basically, most of the investigation on the degradation of the flusher behavior of RPV was related to irradiation. Not too much results was published with the high temperature water and hydrogen effects. And this is a study back in 1994. And the figure on the left hand describes the J curve for the low surface steel, and the figure on the right was high surface steel. And this curve with square symbol was the test conducted in air, and the other three lines were the test conducted in different in the same high temperature water environment, but with different loading rates. And these red arrows indicate the environmental degradation from the high temperature water caused as a reduction from the test in air. And the green one indicates the effect of the loading rate, so it's the mechanical conditions. And if we compare the two figures, we're going to see that the test in air also has a reduction when there's a higher surface content. So it means basically when we're discussing about high temperature water effects, the environment's mechanical conditions and materials all need to be taken into consideration. The other things usually around hydrogen effects are thought to be absent for high temperature, for example 300 degrees Celsius. However, with some previous work in our group, it has been proven that even at a temperature of 288 degrees, hydrogen embrittlement is still possible. And the figure on the left describes the reduction of area with the increase of hydrogen concentration for two steels versus base metal. The second one is the heat treated one, which has a high yield strength. So it's quite clear that with the increase of hydrogen concentration or with a high yield strength steel, there's a remarkable embrittling effects of hydrogen. And in addition to that, DSA can also play a role. So the reds and the orange lines here were the tensile test with the high DSA material, which before and after the hydrogen charging, and the blue and green line were the test for the low DSA steel. So it's quite clear that you can see there's a wider range of wider strain rate range for the DSA, high DSA steel. and the hydrogen betoning effects were stronger in this case. So for when we are investigating the hydrogen effects at such high temperatures, year strength, hydrogen level, and DSA susceptibility are more important parameters. Taking all this information in mind, about 3.5 years ago in Power Institute, we initiated these projects to systematically characterize the high temperature and hydrogen effects on the reactor pressure vessel. So we have investigated 7 kinds of steels, RPV steels with different properties. And today I'm going to talk about 3 of them. The first one is the base metal, which is a reference material, which has a low sulfur content and also low time emission agent. And the second steel has a high time emission agent. The third steel has a sulfur content and high environmental cyst cracking susceptibility. Apart from the test in air, we also perform a test in different high temperature water environments, including hydrogenated, oxygenated, and also nitrogenated high purity water. Both RP and 1T specimens were used in my study, covering the strain rate covers from 10⁻⁶ to 10⁻². And actually, this covers the operational transients and also the loss of coolant accident in nuclear power plants. So this slide summarizes the approaches I use in my work. So flush mechanics tests in air and different high temperature water environments were performed, and simulated high temperature water in nuclear power plants were performed with the high temperature water group we have in our Power Institute. And after the flush mechanics tests, various kinds of characterization were done to understand the underlying mechanisms. So here is the result of the reference material, which has a low sulfur content, also low emission agent. As you can see here, exposure to different high temperature water environments did not reveal any degradation from the test compared to the test conducted in air. And all of the flush initiation resistance was within scale of spacing. So for this reference steel with low sulfur content and low DSA, there's no high temperature water effects. However, for the steel with high DSA, we did clearly observe the reduction of the when the test was conducted in hydrogenated water chemistry. This figure summarizes the flush initiation resistance for the flush mechanics tests conducted at 280 degrees and 250 degrees. And for the test conducted at 250 degrees, with the increase of the loading rate, the flush initiation resistance in high temperature water was decreasing. This was due to the dynamic agent. And the reduction in hydrogenated water chemistry was roughly 20% at 288 degrees compared to 15% at 250. And if we expand the temperature range from 200 to 300, and we can see that there's a minimum flush initiation resistance at around 250, and the biggest or the strongest environmental degradation was around 108 degrees with roughly 20% reduction. So we fixed the temperature and loading rates at this test condition of 288 degrees and 35 micron per minute. And we do the test in different water environments. So oxygenated water chemistry, nitrogenated high purity water, and hydrogenated water chemistry. And it's quite clear that we have the strongest environmental degradation in the of the flush initiation resistance and also the tilting resistance in the hydrogenated high temperature water. After the test, we break the specimen and we see a very distinct change in the flush surface. For the test conducted in air, the flush surface was mainly darker with mainly microvoid coalescence. However, in the hydrogenated water chemistry, a lot of secondary cracks with quasi-cleavage was observed. we were also very curious about the microscopic corrective plastic deformation. So we performed the EBSD corrective for the above four figures were conducted for the test conducted in air. The lower four figures were the test conducted in hydrogen water chemistry. And you can clearly see that ahead of the corrective in hydrogenated water chemistry, we have found a lot of massive tiny grains, which were due to the localized plastic deformation. And also the average grain misorientation degradation was also higher in the hydrogenated water. So this means there's a stronger localized deformation in hydrogenated water chemistry, and this was due to the synergy of DSA and hydrogen. Very interesting when we see the results of the surface material, which has a high sulfur content. The result was totally different because in this case, we have the strongest environmental degradation in oxygenated high temperature water, but not in hydrogenated water chemistry. So this means for steel with high sulfur content, the Krebs chemistry dominates the environmental degradation. If this is right, then if we can further make the Krebs chemistry more aggressive, then we can even observe stronger environmental degradation. To testify this, we, in addition to the test performed in oxygenated water chemistry, we initiate the crack with subcritical strain-induced collision cracking before the flushing mechanism. Flushing mechanism to make the Krebs chemistry even more aggressive. And in some tests, we add 50 ppb of chloride as impurity to further make the Krebs chemistry more and more aggressive. And actually, the test results fulfill our expectation. So we observe with the increase of with the more aggressive Krebs chemistry, we observe the stepwise increase of the fluctuation initiation resistance, and also the area fraction of the secondary cracks and macular voids on the flush surface also increased. Similarly, we performed EBSD accretive of this high surface steel. And as you can see here, that the grain refinement was more severe in the case of normal water chemistry. So the oxygenated water chemistry with a higher grain average misorientation deviation. And this was due to, in aggressive chemistry, Krebs chemistry, we have more retard reconstruction and more dissolution of manganese sulfide, which can enhance the uptake of hydrogen into the materials, and then lead to a higher, stronger localized deformation. So to sum up, for steel, for reference steel with low DSA and low sulfur, we did not observe any environmental degradation. For the steel with high DSA effects dominates the environmental degradation, and then there's a stronger effects in hydrogenated high temperature water. For the steel with high sulfur content, Krebs chemistry dominates, and then there's a stronger reduction in oxygenated high temperature water. Taking this opportunity, I would like to thank Swiss Nuclear Safety Institute, NC, and also some co-workers from PSI and other institutes. Thank you for your patience.